Alright, so this is 7.2, this is volume, and this is actually a huge part of mechanical engineering. Any mechanical engineer would need to use these techniques that we learn because this is how you get odd shapes or manufacture weird shapes. Pretty much anything that has a curved design to it, I mean any part of anything that fits together that has a weird design that's not your normal geometric shape. And even your geometric shapes, you can find areas and volumes using calculus. So today we're learning what's called the disk method. The basic idea, if we just take a very basic graph, like the line f of x equals 3. And that would be a horizontal line at 3. And let's say I'm also looking at the lines x equals 1 and x equals 4. And y equals 0. So basically I'm looking at this rectangle right here. And we could find the area of that rectangle. Couldn't we? Okay. Wouldn't we do that by subtracting the top function minus the bottom function and integrating from 1 to 4? So if we just wanted to find the area of that section, we would integrate from 1 to 4 of 3 minus 0, or just 3dx. And that would find us that shaded area. Okay, but now as far as finding volume, now what we do is we are going to rotate this. We're going to take it and we're going to rotate it around the x-axis. So I'm going to draw a little more three-dimensional. And I'm going to draw it so this is the x-axis, okay, and this will be the y, and, well, this will be the y. Well, it's a little more of a three-dimensional picture is all I'm drawing. Okay. So what we're going to do now is we're going to take that same shape, we're going to rotate it around the x-axis. And when you rotate it, what happens is it becomes circular. Okay, so if you rotate this whole shape like it's a flag on a stick and you swing it around, isn't it going in a circle? Okay, so you have to be able to visualize and imagine that this is actually forming what shape? This is forming a cylinder. So what we're going to do is we're actually going to combine the area between curves with the volume of a cylinder, because now I have a three-dimensional shape. I've taken this flat two-dimensional shape that I can find the area of, and I've all of a sudden made it into a three-dimensional shape. It's a cylinder. And we know the area of a cylinder, don't we? Or the volume of a cylinder. How do you find the volume of a cylinder? Pi r squared h. Okay? Pi r squared h. All right, so, and actually this is what they refer to as a disk. This shape here, now I made it bigger than what their disks are, but their disks would be like taking one little teeny tiny slice of this. Okay, one little slice of this. I don't know if you remember the whole idea behind integration and why integration worked. We spent actually a lot of time, I'm just going to move this aside right now. We spent a lot of time talking about integration as far as how do I find the area under a curve, say from here to here. Remember we talked about making rectangles? We added up, because the area of a rectangle is easy to find. So we started wanting to find the area of this weird shape exactly, and we said, okay, well, I've got all these rectangles, and I'm going to make a whole bunch of rectangles. And the more rectangles we actually made, the closer we were to actually estimating the area. And what we did in the end, we had to do, I don't know if you remember all of the sigma notation that we had to use and the ith rectangle, and I mean, it was just horrible algebra that we had to do. And what we ended up doing was taking the limit as the width of the rectangle went to 0. So we were basically making the width of each of these rectangles 0. So we're basically adding up a whole bunch of lines. So what we're doing now is we're taking each of these lines that we would have added up, or these little tiny rectangles, and we're like spinning them around the x-axis. We're spinning them around the x-axis so they create a little disc. And every time you do that, it doesn't matter what the curve looks like. If I just take this little teeny tiny piece right here, like a CD, okay, and I spin it around the x-axis, it's going to have a teeny tiny little bit of height, which is what we call our dx. That is the height of each of these. Every one of these discs is a cylinder. And we're adding up a whole bunch of different cylinders, and each of them has a different radius. Okay, so like this cylinder right here, this disc right here is going to have a different radius than this one. Notice how this radius is longer than this one? And that radius is guided by that function right there. So what we're doing, the formulas that you wrote down, is a combination of basic integration, area between curves, and the volume of a cylinder. Because what we're doing to create a three-dimensional shape is we're twirling this graph around the x-axis. And when we do that, when we actually draw all of these things, what'll happen is on the other side it'll look like kind of like this shape, and we'll have this really nice kind of weird vase shape. I don't know. So that's actually what we're doing. We're combining area between curves, the volume of a cylinder, and what we learned a long time ago in our book. It's back in chapter 4 if you wanted to refresh your memory or reread it. That's always a good thing. So the formula for finding the volume using the disk method for volume would be, and there were two different axes of revolution. This is the horizontal axis of revolution, and then there is also a vertical axis of revolution. Okay, so here's what the picture that I want you to draw next to the formulas, because the picture is very important. I'm going to require, just like I did with area between curves, that you sketch the area and you sketch the disk, a little cross section of the disk. So in a horizontal axis of revolution, what we have is some shape here. And this is our x-axis, where this is the axis of rotation right here, AOR. Axis of rotation is the x-axis, it's horizontal. What I'm doing is I'm finding my disk looks like this, where this is your dx right here, this height, this is the height of the disk. Basically you're looking at the height of the cylinder. This is the height, which we call dx. From here to here, that distance right there is your dx. Because this height is your f of x, and this is your radius. This is your r of x, which happens to be your function. From here to here is your r of x, your radius that you're rotating around. and you're going to rotate this around the x-axis. And you're actually going to do that with a whole bunch of them along here, but I'm only requiring that you draw one of these. So you need to have a picture like this for every single volume problem you do using the DISC method. Now the formula, what you're going to do then is you're going to integrate from A to B. Okay, so here's A and here's B. You want to rotate this shape right here around the x-axis. You're always going to integrate from A to B. And you're going to take your R of x and you're going to square it. Why would you square it? Because the volume of a cylinder formula has R squared. Your dx is your height. Dx is your height. Now remember, the dx is kind of like a placeholder in here. Your height is so small that it doesn't really count, if you remember what I mean. We're making the dx go to 0. Now, in order to get all of the formula here, you have to then multiply by pi, because the volume is pi r squared h. So the volume of the solid of revolution, basically there's your pi r squared h. But because the radius is changing at every place along here, each of these different things is going to have each of these discs is going to have a different radius, and that's guided by the function squared. And the only way we can get each of those discs is to use the integration. And basically you're finding the area between the function and the x-axis, which is y equals 0. So you're really subtracting the 0. Okay? If it's a vertical axis of revolution, okay, this time this would be your with respect to y. This time your y is your AOR, your axis of revolution. Okay, your key here is that your functions, your radius, it would be you'd be looking at y values. Okay, you would have limits of integration from C to D. And this time your disk would be this way. Your radius would be r of y, and your height would be dy. And you would rotate it around the y-axis. Anytime you rotate around the y-axis or find the area with respect to y, everything in your integral becomes y's. It's that simple. If you're rotating, if you're finding area or volume with respect to x, all of your integral deals with x values. Okay, so here it would be pi still times the integral from C to D, which are y values, and your radius would be an r of y function squared dy. Now this is assuming that your area hits the x and y axis completely. So the first thing we're going to be needing to do, here's our example. What we want to do with this is we want to set up and evaluate the integral that gives the volume of the solid formed by revolving that region about the x-axis. So basically this is all done. They've given us, here's our function, here's our graph, here's a picture of our disk right here. So this would be my dx, and this would be my r of x. And this is my axis of rotation right here. So all I have to do is write the integral. The integral would be from where to where? 1 to 4. And what's my function? What's my radius function? Radical x. This is my r of x. So I would take square root of x and square it. dx is my height, what needs to go out front? Pi.